welcome back. This lesson is the first of several we'll have throughout the year where we focus on determining how much of a substance that we have. Usually for a chemist, that involves finding the mass of a substance, such as how many grams. More on that later in the chapter. It could also mean finding the volume of a gas. More on that later in the course. For now, we'll help to lay the groundwork for those types of problems by determining how many moles, or how many molecules, or how many ions, or how many atoms of a substance. Let's start by reviewing the basics of the mole concept. The following 6 review questions are not meant to require a calculation. Here's the first one. How many atoms of copper are in 1 mole of copper? Stop the video and write down your answer. One mole of copper is 6.02 times 10 to the 23rd atoms of copper. Next question. How many atoms of carbon are in 1 mole of carbon? Stop the video now. 6.02 times 10 to the 23rd atoms of carbon equals 1 mole of carbon. Same question for 1 mole of bromine. Stop the video and provide your answer. Again, 6.02 times 10 to the 23rd. Remember, 1 mole of any substance contains 6.02 times 10 to the 23rd of whatever is the fundamental unit of that substance. And the fundamental unit of an element is an atom, or usually an atom. Consider this next question. How many blank of Br2 are in 1 mole of Br2? Now you can't answer this question until you fill in the blank. Stop the video and write the correct word that goes in the blank. Here's a hint. It's not atoms. Molecules. Since Br2 has 2 atoms of bromine closely bound, the entire Br2 unit makes up a molecule. Stop the video again and now answer the question. How many molecules of Br2 are in 1 mole of Br2? Again, 6.02 times 10 to the 23rd. 1 mole of anything is 6.02 times 10 to the 23rd of the fundamental particles of whatever you're talking about. And for monatomic Br, you're talking about atoms. For diatomic Br2, you're talking about molecules. So far, we've only talked about elements. Some monatomic, where the fundamental unit is an atom, and some diatomic, where the fundamental unit is a molecule. But what about compounds? Again, the first thing I'd like you to do is to complete the question before answering. Stop the video here and fill in the blank. Molecules again. Atoms of NH3 would not make any sense because NH3 is a compound. That would leave us with 2 likely choices, molecule or formula unit. We choose molecule because NH3, ammonia, has 2 nonmetals and is therefore molecular and not ionic. Molecules are the fundamental unit of molecular compounds, just like it was for molecular elements like Br2, Cl2, I2, etc. On the other hand, we use the term formula unit as the fundamental unit for ionic compounds, since they don't exist as molecules. More on formula units in a moment. Now, please answer the question. How many molecules of NH3 are in 1 mole of NH3? Not surprising, 6.02 times 10 to the 23rd. Speaking of formula units, if a compound contains a metal and a nonmetal, it is often ionic, although not always. When it is ionic, we refer to the fundamental unit not as a molecule, but as a formula unit. For example, the smallest unit of sodium chloride is referred to as a formula unit. The purple sphere and the green sphere circled here represent 1 sodium chloride formula unit. Recall from a previous lesson that any one particular cation, like the sodium here, is attracted to all the negative chloride ions which surround it. We could have also chosen to say this pair is a sodium chloride formula unit. It generally is not possible to isolate a discrete sodium chloride particle. As usual, there are exceptions. Bottom line here, refer to the fundamental particle of an ionic compound as a formula unit, not a molecule, and certainly not an atom. So let's apply this. Please stop the video now and answer this question. Again, 1 mole equals 6.02 times 10 to the 23rd fundamental particles, which for an ionic compound is a formula unit. So hopefully you're getting the point here. That is, 1 mole of anything is 6.02 times 10 to the 23rd of the fundamental unit of that substance. To summarize what we have so far, the fundamental unit for an element is an atom, and sometimes a molecule, if the element is diatomic, like I2, H2, Br2, or even other polyatomics like P4 or S8. Note that doesn't include polyatomic ions like nitrate, sulfate, cyanide. Even though they have a lot in common with molecules in that they're multiple atoms that are tightly bound by what we call covalent bonds, we don't call them molecules because they have a charge. The fundamental unit for molecular compounds is a molecule. And for ionic compounds, it's a formula unit. Another side note, if a compound contains a polyatomic ion, like the nitrate ion here in barium nitrate, and the ammonium ion here in ammonium chloride, the substance is generally ionic. And the other key point so far is 1 mole equals 6.02 times 10 to the 23rd of something. Because of this, we can set up conversion factors that relate a mole to how many fundamental units of a substance. In other words, a chemist can begin to determine how much or how many. So, complete the following table where you need to generate conversion factors. The first 2 rows are done for you as some examples. Stop the video now. The fundamental unit of water is a molecule. We know this because it only has nonmetals and is therefore molecular. So, 6.02 times 10 to the 23rd molecules of water equals 1 mole of water. Or, we could write the inverse. We can write similar conversions for lithium nitrate. But this has a metal with a polyatomic ion, so it's ionic, where the fundamental unit is the formula unit. Now that we know how to make conversion factors using Avogadro's number, 6.02 times 10 to the 23rd, let's practice some calculations. How many atoms of lead are in 0.250 moles of lead? Perhaps you can do this quickly in your head simply by estimating 1/4 of 6.02 times 10 to the 23rd. But let's set it up with a conversion factor, because eventually we'll get to ones where it's not so easy to estimate. Here the solution is started for you. Now the question is, what should the conversion factor look like? Consider all the choices below. Select which one is correct and explain what's wrong with the others. Stop the video now. This first one is incorrect. The units are in the correct place because moles would cancel and you'd solve for atoms. But overall it's wrong because there are 6.02 times 10 to the 23rd atoms in 1 mole, not the other way around. This isn't bad, but it's still wrong because the fundamental unit of lead is an atom, not a molecule. This is actually a legitimate conversion factor, but not the correct one for this problem. The 207.2 came from the periodic table, by the way. It's the atomic mass. It's not the correct conversion for this problem because the units don't work out. It would leave grams of lead as our answer, and we want atoms. More on this type of conversion factor in our next lesson. Number 4 is so close, but it's the inverse of what we need. If we left it like this, the units wouldn't work out. We need moles of lead in the denominator to cancel the moles of lead we started with, and we don't have that here. Number 5 is correct. Notice above the problem is solved. Moles of lead we started with cancels moles of lead in the conversion factor, and we're left with atoms of lead. If we do the math, we get 1.51 times 10 to the 23rd atoms of lead. Try this next one on your own. Stop the video now. Here's the solution. Unlike the previous one, this time we need to bring atoms of krypton to the denominator so it cancels the atoms of krypton we started with. Make sure to ask in class if you have any questions. Now try this one dealing with formula units. Stop the video now. Notice two things in this one. First, in the conversion factor, we needed to have moles on the bottom so it would cancel. Also, the fundamental unit of potassium phosphate is a formula unit since it's ionic. Again, remember to ask in class if you have any questions. With this next one, let's stretch your learning a bit. Here's a hint. You'll need two conversion factors. The first one is like the ones we've been working on in this lesson. The second one you'll have to figure out. If you're having trouble, focus on getting the units straight. As always, give it a good faith effort before checking the answer. Stop the video now and give it a shot. Here's the result. Notice this conversion factor is like the others we've seen. Moles goes in the denominator, so it cancels the moles that we started with. This second conversion factor is new, however. Hopefully the placement of the units makes sense. Molecules on the bottom cancels the molecules in the numerator in the first conversion factor. Atoms here in the numerator because that's what we're solving for. We know there are 2 atoms of hydrogen per molecule because of the 2 in the subscript down here. Time for review. Review question number 1. Identify the fundamental particle for each of the following substances. Stop the video now and try all 5, A through E. A is a formula unit because it's ionic. We know it's ionic because it has a metal bonded to a nonmetal. B exists as molecules. Even though it's only an element, it's diatomic and is therefore molecular. C we label formula unit because it's ionic. It contains a metal, magnesium, and a polyatomic ion, perchlorate. It's very similar to part A with the metal to nonmetal, with the difference in C being that the perchlorate ion is essentially playing the role of the nonmetal. D is an atom because it's monatomic, unlike part B, which was diatomic. And finally, E exists as molecules, and we know this because it contains 2 nonmetals. Here's the second and final review question. For parts A and B, I'd like you to just reason out the answer and then write it down. No setup with conversion factors is allowed. For part C, on the other hand, I'd like you to write out the complete setup and solve the problem using conversion factors, like the ones we've done in this lesson. Stop the video now. 1 mole of fundamental particles of a substance is always Avogadro's number, 6.02 times 10 to the 23rd. And a molecule is a fundamental particle of Cl2. Since each molecule of chlorine has 2 chlorine atoms, the number of atoms is simply the first answer, 6.02 times 10 to the 23rd, times 2. Rounded for significant figures, that gives us 1.20 times 10 to the 24th atoms of chlorine. And if we were to do this more formally with conversion factors, it would look like this. Don't forget to ask in class if you have any questions. Well, thanks for listening and see you next time.